afternoon, professors. Today I'm going to present my research project on Markov chains associated with ultraspherical polynomials. Let's talk about some background information and why we are motivated to do the project. So first of all, our study is related to scaling limits and is useful when it comes to connecting discrete systems to their continuum counterpart. One classic example is the Donsko's theorem, where a sequence of random walks, when scaled, converges weakly to a standard Brownian motion. Our paper does something similar to, except it's for the ultraspherical Markov chains, which we are going to define later. The Markov chains we're going to study today is governed by the properties of the ultraspherical polynomials, which is defined using this equation. In fact, there are a family of orthogonal polynomials in the measure here, in the closed interval from -1 to 1. The Markov chain can be defined using transition probabilities described here. In fact, these parameters are in fact coefficients in the recurrence relation relevant to the ultraspherical polynomials. And one of the main goals in doing this project is to generalize the result obtained by Claude George in his 1975 doctoral thesis, where he established this convergence. However, this is only restricted to a single time, where R is the Bessel process. We want to generalize this result to the full process level convergence. Let's talk about first result. Now, to connect our discrete Markov chain to the continuous process, we have to do something called diffusive rescaling. So we define this rescaled function according to dyadic numbers. We want to prove that this rescaled Markov chain converges in distribution to the Bessel process of dimension 2 alpha plus 2, where alpha is the index of the ultraspherical polynomials. Essentially, there are two main steps in proving the convergence. The first one is to prove that it is tight. Essentially, this is a compactness condition. So you want to prove that it does not escape to infinity or have some pathological oscillations. The second one is the finite-dimensional convergence, which is described here. Because the process is Markovian, it suffices to prove the convergence of the transition semigroup. The first criterion for tightness is the pointwise boundedness, which is described here. The second criterion is a control of modulus of continuity. Essentially, this means that the chain does not oscillate too much over some small time interval. We focus on the second criterion, and we shall first introduce some preliminary results. First is the fourth moment bound. We consider any starting state A, and we can decompose x minus A into a martingale term in a predictable drift process. Our approach is to use the BDG inequality and the Minkowski inequality, which allows us to use the property of the ultraspherical Markov chain and bound the expression as follows. And for the second lemma, we take the fourth moment bound, and we use it to control the fluctuations over some time blocks. We use the Markov inequality and the Dupes inequality to obtain this inequality. So we conclude using the law of total expectation and the Markov property, and this is what we obtained. And next, we globalize the result from the previous lemma. We control the fluctuations over anywhere in the time interval. So the idea is to partition any time interval into blocks of dyadic sizes. So like this. We consider any state K and L subject to this condition. We can see that they are either on the same block or in two adjacent blocks. So by triangle inequality, we can conclude that this event is included in this union. So we apply the union bound and apply the previous lemma with some rescaling. We can obtain exactly what we needed to prove tightness. Now let's move on to proving the finite-dimensional convergence. We consider the set of dyadic numbers and consider any sequence of starting state restricted to a compact set, which is strictly positive because we want to avoid the boundary 0, which is because the boundary condition is a little bit complicated. We define the continuous semigroup action and the discrete semigroup action. We want to prove this convergence. To prove this, lemma, the main tool we're going to use is the dominated convergence theorem. We rewrite the sum into a single integral, and we find an integrable function which serves as a dominating function, which allows us to apply the theorem and write this limit as a single integral. After evaluating the integral, we can find that the integral can be written in this form, which is a known form actually, because we can apply this identity, which is a known result. After simplifying the expression and manipulating, we can get the convergence that we wanted. In fact, the continuous semigroup action can be expressed using the transition densities. Now, to conclude the finite-dimensional convergence, we simply used induction, and that's it. Now we move on to considering the first heating time and exit time. They are defined as follows. For a point B, the heating time can be defined using such an expression. Now the exit time of an interval BC is defined as follows. Now we define a function u, which is called the lambda potential. That's an interesting observation, is that we can construct two eigenfunctions using the lambda potential and the ultraspherical polynomials. And we obtain these two eigenvalue equations, which is going to be very useful in the proceeding analysis. Now, one of our main tools when studying heating time and exit time is the Laplace transform, because we do this because it's convenient under Levy continuity theorem. Consider any state B and the starting state A. You can see the two cases. The first is the upward passage. The second is the downward passage. For the first case, the Laplace transform can be expressed as a ratio of ultraspherical polynomials. And the second one is the lambda potential. The reason we are using two different type of functions is because of the boundedness condition. Because the lambda potential is inherently bounded. We can see why. Now for the upward passage, we construct a martingale, which is bounded. By the optional stopping theorem, we can apply the definitions directly and rearrange, and which use the ratio of the eigenfunctions. The concept is similar for the downward passage, except we cannot use the ultraspherical polynomials anymore. We have to use the lambda potential, and applying the optional stopping theorem again, we obtain the ratio of the resolvents. Now, you can actually prove that the heating time under some appropriate rescaling converges in distribution to the first passage time of the Bessel process. The proof can be done by using the Laplace transform introduced before, as n tends to infinity. The concept is similar for the exit time as well. First, we set up two martingales. First using the Legendre function, and the second using the lambda potential. And then applying the optional stopping theorem, we can obtain a system of equations, which allows us to derive the explicit expression for Laplace transform for discrete exit time. Now we compare this with the already known Laplace transform for the continuous exit time. Now under Levy's continuity theorem, we can directly conclude the convergence because the limit of the discrete transform under some appropriate rescaling equals to the continuous transform. And that wraps up our presentation today. Thank you.